reactions.
S. What we see this time is that for every action, there is an equal and opposite reaction. Newton's third law of motion. Alexander pushes against Pedro, action. This causes Pedro to move, reaction. At the same time, Pedro pushes against Alexander, action, causing Alexander to move in the opposite direction, reaction. And they moved an equal distance, action, equal, opposite, reaction. The battery.
What was wrong with that last bit, which is so typical of these videos? I'll play this one more time.
To move in the opposite direction, reaction. And they moved an equal distance, action, equal, opposite, reaction.
And that last, well, sentence before the last. I tried?
The stickmen have ears.
They do have very, well, how would they hear?
Well, they don't need to hear, they're just pushing.
Oh, they're
And why do they only have ears and
That's
eyes?
stickmanist.
I've worked it because
They need to perceive their surroundings.
Then they need a nose.
Well, stickmen, they don't, that's kind of rude
And
to
then
say,
they
but
mouth
stickmen don't
too.
smell very good.
True.
And of course, they don't smell very good because they don't have a nose. All right, so why? What was it in that last bit that was wrong? One more time.
they moved and equal distance.
Okay, here.
Action. At the same time, Pedro pushes against Alexander, action, causing Alexander to move in the opposite direction, reaction. And they moved an equal distance, action, equal.
They did not move in equal distance.
They might have, but who cares? Right? Why did they move in equal distance? Because they hit the wall. It has nothing to do with Newton's third, right? So she said distance when she said they moved with different accelerations and the same mass, da-da-da. So they usually, it just messes that up. So yeah. So again, it has nothing to do with distance. It has nothing to do with speed. Those are mistakes that are so common to this. I literally, it's going to be a little bit different, but I literally argued my son's high school physics teacher to the ground on this, because he had a misconception on this too. My son then went to a different school. Moving on from there. It's actually true. There's a lot of other reasons other than that guy, but that was one of them. The science department was, woo-hoo. Anyway.
Opposite reaction. The battery's mass is about 80 kilograms, so now the force is the same, but the mass is different. Remember Newton's second law of motion. Action and reaction are caused by the same forces, but they're expressed through different mass. Therefore, Alexander moves less. Let's see what this...
Okay, here comes some bad examples. Watch this.
I'm
Okay?
so excited.
Here we go.
Here we go. This is like Pedro and Alexander on board the station.
Twice the mass on the
We have
left.
another girl, and they don't travel as far.
So yes, the concept of sound, the demonstration is lousy. Because these people literally hit the brakes.
Yeah.
But you could certainly see that she accelerated faster away. Who was pushing in this scenario?
Oh.
Yeah, exactly right. You gotta go home screaming both. In your sleep, you're gonna be, oh! Why are you screaming both? Oh, it's like, oh, I can't do that. But yeah, they both push, right? And in this case, they really do because they both do this. But even if she had her back to these two, they would both push equally as hard. The force would be one force. Trust the force, Luke. But there would be equal and opposite reactions. Not equal in speed, but equal in mass times acceleration. Newton's third law rules again.
The force of throwing the ball makes her move backwards. Not travel as far.
This is actually a better example than the guy did on a spaceship, because you can really watch as they throw forward, the ball throws them backwards. Right? You can really watch them move.
The force of throwing the ball makes her move backwards.
Right? Yeah. Now, I'm going to show you these because these are excellent examples of momentum. Not really good examples of Newton's third. But momentum's next, so hold tight. But these are really good examples of momentum. Here we go.
A collision. That's a force. But do you know why only the guy in front moved?
Now, just explain that with Newton's third, because he can. It's a better example of Newton's momentum, which is why I argued, I can't remember his name. Good thing. Anyway, that's why I didn't argue with what's his name about. I explain this with Newton's third, because Newton's third's here, Newton's third's everywhere. You are Newton's thirding as you speak, because the chair is pushing up on you. You're Newton's third, otherwise you'd be falling to the center of the earth. That'd be hilarious, but hard to teach. So, the chair indeed is pushing up with you with that normal force. Remember, there it is, looks like a logic. Okay, so explain this with Newton's third, go.
Okay, so person in back moves forward and pushes second guy. Second guy, well, he's getting pushed now, so he moves forward and he pushes the next guy. Now third guy, he's getting pushed now, so he moves forward and he pushes the next guy. Now fourth guy, he pushes the next guy. And the last person, he gets pushed too, but like now he can't push anyone else, he just keeps going forward.
So he just keeps going forward. Okay, good. Now, how is that Newton's third? So how is that Newton's third? Because that's actually what you just described as good, but that's almost more momentum. This person gave momentum, whee, right? So where's Newton's third here? This is the trickiest part. Go ahead, what do you think?
They're all pushing each other, and then the sixth person, well, the last person doesn't have someone to push him.
Yeah. She pushes him and he pushes her. That's mean. He pushes him, he pushes him. That's mean. Blah, 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 right? So they do indeed push each other. This poor guy has nobody to push him. Poor little guy. Nobody pushing him around. So he just goes zipping off away from his pushy friends. Go ahead.
I don't think that was really a fair experiment, just because they were some people were pushing extra, so they might have a resulting force that is more than the previous.
Yeah, these are good. Another thing here, you won't remember this by the time we get there, but I'll throw it at you anyway. Later in the year, we're going to be talking about two different types of waveforms, longitudinal and transverse waves. A longitudinal is a wave that actually does this, where it moves through, the wave moves in the direction of the group of people. So she gave this group energy. That energy was transferred to him, to him, to him, to him. It's transverse, and the energy that she gave was transferred through all of these people. It's a transverse wave. More on that, or I'm sorry, it's a longitudinal wave. More on that when we get there, and I'll forget that I gave you this demonstration, and so will you. But there it is. We got it there.
The students are arranged in what we call a Newton's cradle. The skater collides with the first student, action, and onto the...
Just forward a little bit. Oops, sorry. Also, excellent example of momentum. That's so much Newton second, Newton third, we got.
This is like the guys on the ice.
So he gave the ball momentum, it's mass times velocity, we'll get to that probably before the end of the day, mass times velocity. It collides into this ball, which gives it momentum, divides into this ball, which gives it momentum, collides into this ball, which gives it momentum. Momentum is transfer, it's conservation of momentum. We'll get to that in a little bit, because momentum cannot be lost.
Only the last ball moves.
Now they've got two spheres at the end here. When they smack this sphere, both of these spheres are going to get the same amount of momentum that this sphere had to begin with. So if you look carefully, and I mean really carefully, you'll notice that this guy is going with more than likely twice the velocity as these two will result in. So watch very, very carefully.
And here the two...
It's hard to tell because you can't see, but that's what's going on. It goes with half the momentum, half the velocity because it's as much momentum. But momentum, again, is conserved. Momentum is mass and speed.
Balls are moving, but they don't seem to go as fast. This is because the same force is traveling through the cradle, but is expressed through twice the mass.
Twice the mass, half the speed. Oh, wasn't that called an inverse proportion? Yes, it's back again.
As mass and acceleration are related, the two balls travel less than the single ball.
And they have less velocity.
The third law helps us in other...
Anyway, so, never makes you feel like you know a concept when you can yell at somebody else when they mess the concept up. So there you go, kids. All right, so, little Newton's third law there. Good. Now I want to do... How do I want to do this? Let's do it this way. Okay, so let's try to see if we can get some of these wonderful experiments actually in this classroom. So here's what I want to try to do. All right, so, go ahead.
So can I push something?
Yes.
Yes.
Hold on. All right, so, here's what I want to try. So with this chair here, go ahead.
Can we line a bunch of people up and then one person pushes them and they all fall over?
Yes, sign your waivers, kids. No, that's not it. So what I want you to do is we're gonna do this in the back of the room because we've got room back here. But that means if you guys could just take your tables and have, basically tables and chairs on the carpet. That way there's plenty of room to do what I think we can do with this. Just kind of move this. Good. All right.
Together and you keep it balanced.
Good. It's also teamwork, camaraderie. Somebody like you. Okay, so let's do this. So what I have brought for you, here's some physics fiends. Friends was better, wouldn't it? All right, what I brought for you, Fearsome Physics friends, is 2 skateboards. All right.
Well, that's what they're for.
Let me give you a little bit of information about what we want to do with these, or a little bit of safety and tips on this. So these are skateboards. Thing number 1, don't stand on the skateboards. Some of you may very well be expert skateboardians. But even if you are fantastic skateboardians, you may still fall on your head, and that's bad. Jim likes to avoid those things because Newton's third law says, ouch. So, no falling on heads. Actually, that's the next concept is ouch, but we'll get to that in a second. So, A, please don't stand on these. B, when you sit on these, which is what you're going to do, is notice these screws here. This is called the truck. The truck is the wheels. These screws hold the truck on. Kind of makes sense, doesn't it? However, if you sit on this side of the truck, it's then called a fulcrum, and this is called a lever, and it goes like this, right? Yeah, so don't sit there. Sit on or in front of the truck. I will give you a small demonstration.
Wow, I can't.
So if I sit in front of the truck, oh, nice and safe and sound. If I sit behind the truck, hey, don't do this at home, kids. All right, you've been warned. Okay, so that's thing number 1. Thing number 2, or 3. I've lost count of my things. All right, yeah, this over here. In this case, here's what we're going to do. This 2 different ways. So 1 should work pretty well on here, I think. All right, we're going to have 2 people sit on the skateboards. One person sit on this one person sit on this one. In both situations, the people are going to sit facing that direction. Okay? So one person's going to be facing away from the other person. One person is going to push the other person. Was that a fair statement?
No. They push each other.
Oh, somebody just said, right, because of Newton's third law, they both have to push. But one person will be the physical exerter of force in this case. But both will indeed push. Okay, good. Okay, so, and then we'll just kind of see what happens. This room is nice and flat, so we should get some good results on this, I think. At this skateboard might be a little slower, but we'll see. So first off, we just need 2 willing volunteers. My, you guys are heading fast. Come on up, kids. So pick whichever skateboard you want to sit on, do face in that direction. But one of you will be in front of the other of you. Everybody's glasses really big. 4, actually. Wait, hold on. I had one when I didn't even think that I could have one of them when my son was 7 years old. These aren't them, though. All right, those are pretty beat up. Okay, so now this is you guys are like the biggest class I've ever had trying to do this. This is pretty weird. Okay, so yes, so what's going to happen here is Benjamin's going to push Max. So James, you might want to move.
Yeah, you might want to move.
That's a thought. All right, so Benjamin's going to push Max, and I just want you to kind of see. Actually, they're both going to push each other, even though Max doesn't even have his arms out, but he's magical. Okay. Or in this case, legs out, apparently. Don't push too hard. We don't have them. You didn't sign your waivers. Okay, so whenever you're ready, go ahead and do push. Yeah, okay. All right, so you saw what happened there. Okay, good.
Yeah.
So you definitely saw an opposite reaction. One went one way, one went the other way. Did you see an equal reaction? The answer is yes, but how is that an equal reaction? Right? You want to try it?
Same amount of force, but different mass.
Different masses, yeah, exactly, we've got different masses here. So Max didn't go as far, right, as Benjamin did, good. Well, let's try that, so go ahead, you guys, hop on up here, if you'd be so kind. All right, everybody, thank you very much. Let's get like 2 more volunteers, and I'm curious, and that should smooth things. Okay. No, these all feel pretty good. Okay. These are relatively new. I didn't buy them, but they're relatively new. All right, so, you want to try?
Yes.
All right, James, who else wants to go with James? Who wants to let me push that?
Oh, I know it.
Go.
All right, good.
I've
Thank you, guys. What did you do? Okay.
Sport is weird.
Oh,
Okay.
wait, actually, turn out the other way, Dylan.
Oh, sorry.
Just to emphasize the fact that you're pushing without pushing.
I still.
Good. There's the track thing.
I still have the.
Everybody keep your hands in place.
No.
All right, you guys might want to move just in case.
Yeah, Oh, I did it.
Good.
I
Perfect.
realized it's gonna be less unstable when.
Oh, you guys are fast. Okay, so whenever you're ready, kind of say 1, 2, 3. Ooh, careful. And you move forward and touch. Good. All right, whenever you're ready, say 1, 2, 3. Give Dylan, and Dylan will give you a push.
1, 2, 3.
Yay!
So again, we got pretty good there, right? We got pretty good. Okay, so I wonder if we could do. How else could we do this? Just for fun, let's try it this way. Dylan, if you don't mind,
Hi.
hop on that one,
Not one.
and I will hop on this one. Since I
Okay.
think in this class I am probably the lightest one here. So here we go. All right. Lightest one, eager and willing to put himself in pain. Okay.
Oh, God.
Whenever you're ready.
Good luck. Stop.
This is not going well.
Yeah.
We need to put on this race that died in the name of science.
That's right. Same way, just kids.
Oh gosh. I'm rolling away.
See, I'm already forced.
2, 1, go.
All right, very nice. I pushed so hard I knocked you over. Look at that. So, right, equal and opposite. It doesn't look equal because I moved way faster than Dylan moved. But remember, equal means mass times acceleration. We are Newton's second law here again and again and again. I do want to do this one more way, slightly differently. So we're going to have 2 more volunteers. Anyone want to try to run that? All right, Gabby, come on over. And then who else? In this case, I don't think masses matter. Do I try? Yeah, come on. So in this case, we're going to have you guys spread out a little bit. So we're going to have one person on this side, the other person a little bit down the walk here, if you will.
Facing which way?
We're going to both, in this case, both face in the same direction. Sometimes this works and sometimes it doesn't. So go ahead and have a seat, if you will. Remember, be aware of the. Oh wait, actually, both. Sorry, I didn't have bad instruction. Both face towards each other, I should say. Same direction, meaning at each other. Okay. There you go. You have an end of that rope, and you have an end of this rope. Now remember, one of the things I said before is Newton's third law is an equal push and a pull. We haven't really seen a pull yet, except for the guy with the battery. But let's see if we can make this work. The best way to get this to work is basically to kind of give a nice, constant, but not too fast pull on that rope. And then hopefully we're going to see what happens. Right, so we'll have, Gabby, you give it, and you just hold tight, right? And give a nice, constant pull on the rope. Let's see what happens here. Yeah, that's working pretty well. At a certain point, you outspeed the rope. But we were able to see that they were both moving, right?
Yeah.
So very nice. So Nadia was not pulling, she was just sitting there, and yet she was indeed moving. Go ahead and move back again, and we'll see if we can reverse this. And so I think one of these skateboards is a little bit easier than the other. So in this case, Nadia, you go ahead and give it a nice, steady pull. Let's see what we can have. Yeah, eventually you have to speed up, unfortunately, but you can see, because eventually you're going faster than the pull is. But good. But again, you can see that we had that situation happening, and we had those coming together there too. When this works really, really well, and it's hard to do, but I've had 2 students do this, and you can actually almost assess their weight because it's a ratio. Because one student will move a lot more than the other one will. You can assess the weight of the 2 students that way, which is kind of cool to do. But that's hard to do because the skateboard move faster than you. Does anyone else want to try it before we put these up? I hate to deny you the pleasure of sitting on a skateboard in the middle of physics class. You want to try it? All right, come over, guys. Yeah. Thanks, you guys. Participate. I appreciate it very much. All right. So come on up. We'll do the same thing. We'll have you guys be pullers. I think we should police. We might be doing police or pullers. Those are shiny shoes.
That's like back to the future.
Look how polite man you get back there.
Well, we could change that.
Okay. Now, which one are you guys gonna pull?
Okay.
Okay. Kind of nice and steady.
What would happen if I touched the rope?
Not bad.
Die.
We had it there for a bit, didn't we?
Yeah.
And then for some reason that one stopped for some reason. But we certainly had it there for a bit. Good, good, good. We'll just do it again the opposite direction there. This time, Benjamin, you give a tug. That's actually slow. I shouldn't say tug, slow. Nice, slow pull.
Mine is not Back to the Future.
Perfect. That's exactly what I'm looking for. Perfect. Good, good, good. Yeah, that was ideal. Yeah. It is not easy to get that to work. Good, good, good. Anything else? All right, kids. Nice, thank you very much.
All right, do a backflip wall on a skateboard.
No. I was able to work on
You can do a
how.
front flip though.
I had about a 3 or 4 inch and 5 or 6 inch tolerance. Really working this. Thank you very much. Way back when. Yeah, like 40 years old, a 40-year-old jumping up and down with skateboards. I only got the skateboards because my son really wanted to do it. He was like 7 years old and I couldn't leave him alone at 7 years old. So I'm just sitting watching him skateboard. I'm like, I'm not going to just sit here and watch. How lame is that? So I got a skateboard and rode with him. So this 40-year-old guy out with a bunch of teenagers and a 7-year-old. So I'm not too sure which was lamer, but at least I was getting exercise. And actually the kid thought it was great. I'm like, dude, I wish my dad would skateboard. A couple of them said I wish my kid would skateboard, even though they're only 14. That was a little creepy. So, who we got? So, just kidding. All right, so that's Newton's third law. I want to push this a little bit now to show you how earlier I made the outrageous claim that Newton's third is really just 2 Newton seconds shoved together. Watch this, kids. So, seconds ago, we had 2 people sitting on skateboards. Skateboard 1 and skateboard 2. Like so.
Wow, this is great. Hey,
So it's supposed to be a pair of arms, like going like this. All right, so skateboard 1 and skateboard 2, and then the person behind is a gibbon. Okay, so when this person over here pushed this person was the only one pushing, right? Wrong, they both push. Yes, thank you very much, my disciples. Okay, so indeed, they both pushed. So there was one F. There was one F, right? One F, right? Okay. So there's one F, but look, there's a mass over here, and there's mass over here. Mass 1, mass 2, right? So when this F causes this M to A, it's going to accelerate, and it's going to accelerate. Look, kids, Newton's second. Newton's second mirror image. Just Newton's 2 Newton second laws shoved together. And notice, I keep saying at the very beginning here, that equal is the equal of mass and acceleration, because force must equal ma. They equal each other, right? Force equals ma, right? Just like when you guys get up in the morning and your ma has to yell at you to get out of bed, force equals ma, right? Okay, that's how that works. Do your homework. Force equals ma. Okay, good. All right, so, so now the thing here is then, took a half an hour to do. If I've got this force, all right, this mass is a bigger mass, right? We'll say I contacted the WWE and I had I had Dwayne "The Rock" Johnson show up in it. So Dwayne "The Rock" Johnson decided to take part in the Chapel Hill physics experiment. That would be awesome. All right, and he sits down. He's actually a pretty nice guy, although he's really mean. He's one wrestling persona. So in other words, Dwayne "The Rock" Johnson would have an M that would look something like this. Okay, there we go. All right, so there's his M, right? Let's say I'm the one who sits on the other side, compared to Dwayne "The Rock" Johnson. There we go, okay? So in this case, okay, there you go, right? Okay. Now, they'll say, I'm the one who pushes Dwayne "The Rock" Johnson. Is that the right comment? No, because you both pushed. You guys are so good at this. So indeed, I got enough. I push Dwayne, and Dwayne goes, yep. Right? He barely accelerates. He's like, is there a, you know, is there and then I go, down, right? See? Because depending on how much I pushed him, but again, these would be, oops, mass is so small I left it out. These would be equal. The opposite is direction, positive and negative, if you will. But because there's this force, these can't be anything other than equal because they stem from one number in the middle. Let's do this again with a little bit of numbers on this. All right. So, again, oops. So let's just make the math easy and let's just say 12. Because 12 is a wonderful number because it's divisible by so many things. So let's just say 12. So in this case, we put Dwayne "The Rock" Johnson on here. It's so much fun to say Dwayne "The Rock" Johnson. All right, so this is the F. So Dwayne has a mass of 12, we'll say. I have a mass of 1, we'll say. Okay. So now, this is my M. This is his M. So his acceleration is going to be? 1. Yeah, do it. 1 times 12 equals 1, kids? 1. That's right, kid. Okay. And in this case, 1 times 1 equals 12. 12, right? So his acceleration is going to be that. My acceleration is going to be that. Notice it has to equal that 12 in the middle. Right? Okay. Doesn't matter how hard either one of us push, because he pushes as hard as I do. If I've got Dwayne on this side pushing me, it doesn't matter, although this number might be slightly larger, but it's not going to matter, okay? So yeah, so they're going to be the same. So in this case, let me just play with this a little bit more. Let's say now, we won't have Dwayne "The Rock" Johnson, we'll just have somebody else be on here. But now we'll have a 2, mass of 2, and over here it's a mass of 6. So now what do we see? We see a 6 here, right? And we see a 2 here.
Yay!
So, yeah. So we're going to just Newton's second law. And notice again, we've got an inverse proportion here. If this is equal, as one goes up, the other goes down, or vice versa. Right? It's inversely proportional. So that's what happens there. So that's why this Newton's third law is often so confused, because you don't see it being equal. Right? Dylan didn't move nearly as much as I did. Right? That didn't look equal. But if you add it up, those would be equal responses, assuming the skateboards were equal, which I'm still not quite sure, although they sure seem that way, but they don't act that way. Anyway, so that's really Newton's third law in a nutshell, right? Equal and opposite reactions. The thing that makes it strange is this idea of they don't look equal. They don't perceive, you can't see the equal necessarily unless they're the same masses, and they're hardly ever the same masses. So that's how that works. Okay, I want to bring you forward here. Yeah, I have to take you forward a little bit. Wasn't sure we're going to get to this or not today, but I guess we can. Often with Newton's third, momentum's taught on the same time. I usually don't do that, but you guys are cruising along here, so we're going to introduce you to this idea here. So today's other word is momentum. Momentum. Oops, sorry.
What happened?
Can I bring a video up for you for a second? There you go. Momentum. Okay. So, momentum, definition of momentum, often, is inertia in motion, which is a fantastic definition, easy to remember, however, it may not make any sense whatsoever. So what does that mean, inertia in motion? What's inertia? What's that?
Inertia.
Can almost define it in one word, which is fine here. Inertia was basically, what's that?
Mass.
Yeah, basically mass, right? I like to think it's a little bit more than mass, but often mass is how it's defined, and that's fine. It's especially fine here. So inertia is always with everything that has a body. From an atom, which has little to no mass, to this building, which has a whole lot of mass, right? Inertia is a thing. The more inertia something has, the harder it is to get it to change its motion. Newton's first law, okay? All right. For something to have momentum, it must be moving. So I'm going to give you a, yeah.
What would your definition of inertia be?
My definition of inertia really is how hard it is to get something to change its motion. Yeah, and by how hard I mean how much force. Yeah. Which really is just mass, but if you tell somebody inertia is mass, that doesn't, that's just another word for mass, and that's just another word for weight, and that's all wrong. So, so I pulled that out a little bit. But if you ever look up momentum on the Wikipedias or ask Siri, what's momentum? Oops. Oh, nobody's phone turned on. Perfect. Okay, good. So, okay, Google, what's momentum? All right. Happens to me in the car all the time. Drive along, it tells me stuff. Shut up. All right, so momentum is inertia in motion. So the difference, this will definitely be a quiz question, difference between momentum and inertia is momentum is all things, always have inertia. Sorry, big definition here. The things must be moving to have momentum. Because they're kind of confusing. Because they both have to do with how easy it is to get them to move, how easy it is to get them to stop moving. So it's easy to confuse the two. The other difference between momentum and inertia is momentum is a quantifiable property. In other words, we can math it. Oh, joy. Oh, more math, Jim. I know. You can sense the excitement. That's how in touch I am with my students. I can totally know what they want. Okay. Okay, now, you guys written that all down? Close to it? Somebody was here writing. While you're writing, I'm going to go to work. Because one of the neat things about momentum is that the formula is kind of right there. So, this is going to be very, very silly. But there's a reason for that. Silly in your class, Jim? You're normally so sedate and serious. I know, but every now and then, I like to let my hair down. All right, so let's say, there I am at the bottom of a ramp. And let's say, at the top of the ramp, oops, don't get ahead of yourself there. At the top of the ramp, I put a ping pong ball. Oh, you're doing a ping pong. Okay. And I let the ping pong ball go down the ramp. And I stand at the end of the ramp, and down goes the ping pong ball. And it hits me right in the ankle. Okay. Now, let's say I get a bowling ball. And I put the bowling ball at the top of the ramp. The bowling balls always look surprised. There's the bowling ball at the top of the ramp, and let it go, and it rolls down and hits me in the ankle. Which one of these is more fun for you? And less fun for me? The bowling ball, right? You can say it, it's okay. I know my students. All right, so yeah, the bowling ball is much more exciting, right? Because the bowling ball hits me, the bowling ball causes more force, perhaps even a broken ankle. Why does the bowling ball cause more issue? Without giving things away, what should I think?
Pulled down by gravity before force.
It's pulled down by gravity. However, remember, gravity accelerates all things equally. So theoretically, if I drop that ping pong, this would have to be in a vacuum because it's a ping pong ball, but if I drop the ping pong ball and the bowling ball, they both hit the ground at the same time.
Yes, this has one has had to be accelerated with more force.
Right, and because it has, go ahead.
It's more inertia.
Yes, good. So more force, more inertia. So this thing rolls down the hill. When it hits me, it has more mass. Bottom line, this has more mass than the bowling ball does. Theoretically, it won't, but theoretically it should hit me with the same amount of speed. It should accelerate equally because they should stop at the same amount of speed, which means that the force would be the same, except that the mass of the bowling ball is so much bigger, right? Okay. Now let's do it this way. Same bowling ball, same surprise expression on its face, different ramp. So in this case, we've got ramp A boop, boop, and ramp B. Boop, boop. Now I let both bowling balls to go down the ramp. Which one hurts more now?
Depends on the order of shift.
Well, which one? Go ahead.
A,
Why?
because it's got more acceleration.
It's going to have more velocity, right? When it hits me, right? Because it's raised up a little bit more, so it should have more. It should have more velocity. So more velocity. So the more mass and the more velocity equals the more pain. That's literally the formula for momentum. But Jim, momentum doesn't start with the letter P. I know, but everything else does. Miles, mass, meters, all starts with M. So they use the letter P to stand for momentum. They really do. So I just like to say it equals pain because it does. The more momentum something has, the more pain it's going to exert. Right? Okay. So, and the other fun thing about this is if I put a little O here and I put a little E here, it literally spells the word move, which is what momentum is. It is a quantity of movement. This is where Newton started this whole thing of Newton's laws, is this idea of a quantity of movement or momentum. Quantity, like quantum, a quantity of movement, of moment, of movement is what that means, which is kind of cool. Okay, more on that, quite a bit more on that, probably next week since we're cruising. We'll see. Okay, so that's the idea with momentum. Okay. Now, I'm going to show you a little video here which does a really nice job giving you this in some more fun terms.
Good video.
No, this one's a good one.
Mm-hmm.
Oh, they're all. I hope I can find this one. Oh, that looks cool. That's what I want. That looks really cool. I don't know if I can find you. No, I'll bring this up, but the back part ready for this yet. Open link in a new tab. Where's my good momentum video? How to play games, Linkin Park, Arcane. Let's see, where's my good momentum video?
If you're sharing a hotel room with friends, you're also sharing a
Historic first steps back.
I was going to show you this. Can't let Newton's law go without showing you this. Some great examples of Newton's laws. I almost stepped through this a little bit too quick. But some great examples of Newton's laws are, a rocket, right? That's one of the ultimate examples of Newton's laws. Other good example of Newton's laws is blowing up a balloon and letting go of it, right? Because you have force pushing in one direction. You have force, the part, right? And you have an equal and opposite reaction. Air going one way, the balloon going the other way. Another really, really good example of Newton's third law is this idea of shooting a gun, right? If you ever shot a gun, you may have noticed that when you shoot, they've got a little bitty teeny tiny bullet that weighs maybe 30 grams, depending on what caliber you're firing. You're also holding a gun that's going to weigh probably kilogram-ish, depending on what you're firing. And then and it's connected to your body, which weighs 120, 130 pounds, 67 kilograms, depending on you. All right, in this class, a lot of kilograms. You guys are all big. I mean, you know, big muscular people in this class. So when you fire that gun, right, what happens is that there is a force. What's the force in this case? What's going to cause the force?
The explosion.
The explosion, the gunpowder, right? Bang, right? Remember your kids. So yeah, there's going to be a big bang, right? That explosion force is equal and opposite. So there's an equal and opposite here. The equal and opposite in this case is the bullet in one direction, the gun in the other, right? So when you're holding that thing and fire, right, the bullet goes that way, really, really fast. The gun goes that way, not quite as fast. Why not? Why do we have those differences in acceleration here? Or try it?
Because one has more mass.
Yeah, right? Masses are hugely different. That's my big M and my little a that I had up here a second ago, right? Because the mass of the gun is relatively large, especially when it's connected to me as a human being, it's really quite large. But if you've ever fired, you can feel that, right? So that's called a recoil, but that's literally Newton's third law, that push back. Good friend of mine, tell you a quick story here. Good friend of mine years and years ago, I mean 40 years ago, give or take, took me skeet shooting. Have you ever been skeet shooting? But the skeets are these, they're not animals, there's that thing called a skeet. A skeet is a pigeon. Well, it's a clay pigeon, these are the discs. And you put it in this little frisbee shooter thing, and you say pull, and it goes thump, 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 thump. And the little frisbee thing goes whee through the air, and you're supposed to hit it with the, well, you're supposed to shoot it. You're not supposed to hit it with the gun, because that would be weird. You're supposed to shoot it with it. All right, so, but off it goes thump, 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 thump. And then you're supposed to hit it with the buckshot and fire. Well, shotgun's big. I've never seen a shotgun before, but they have a tendency to be big. And a skeet shoot shotgun is really, really, really big. And my buddy was huge. It was pretty funny, because in high school I was maybe 90 pounds. And my buddy was 250 pounds. So it was like, hello everybody. So so he takes me skeet shooting, and he'd skeet shot a lot, Scott shoot a lot. I don't know. He's an excellent marksman. He actually went to the military to be a marksman. It's fantastic. I was not. I had never shot anything before in my life other than an occasional spitball. So off goes. So he's like, okay, Jim. Now here's. So he does the thing, and he's like, watch this, and shoot. He fires like 3 of them out of the air without any problem whatsoever, because he's a big, big boy, right? So he's like, okay, Jim, here. And he hands me the shotgun that isn't a whole lot smaller than my gun. So, okay, right? Now what do I do? He's like, okay, watch. The first thing you must do is when you take the shotgun, you have to take it and you have to put it against your shoulder really, really hard. Because if you don't put it against your shoulder really, really hard, what happens? Your shoulder is in somebody's car. Yeah, because you have to put it really, really hard on the shoulder, because exactly, recoil. It's a big gun, but it fires with a huge force, right? So even though it's firing buckshot, which are little bitty things about this big, about, I don't know, 150, whatever it is in buckshot, but that recoil is huge, and sure enough, I was scared out of my mind. It literally was maybe 90 pounds, about that tall. And I'm holding the gun, and then, you know, I was standing, I was over-prepared, because I knew this was going to hurt. But really, wham, it was like getting hit by, getting hit by a strong punch. It was pretty intense. And it was pretty neat. So and eventually I actually hit a few, and when we skeet shooting again, I didn't get anything. But anyway, fun sport, actually. So, but that's that whole idea, and if you've ever had that experience, you will have known that that's Newton's third law. Another good example is I gear this up. Because we don't want to do this entire video because it's too long. Just sit, no, back up. Get right around here, back up, right around here. So another good example, have you ever seen the movie Wall-E?
Yeah.
Right? Yeah, right? In fact, it's over here someplace, right? So in Wall-E, poor little Wall-E gets lost outside of a spaceship. Right? He has to leave the spaceship or something at some point in time, and Wall-E's lost in space forever. No! Because Wall-E knows Newton's third law. So what does Wall-E do?
Oh, he's the fire extinguisher?
He's the fire extinguisher. Yeah, and that's really true. If you use the fire extinguisher in space, indeed, if you directed it in the right direction, it would tell you exactly, it would force you exactly where to go. You have to be a little careful with that, although I think they did it right in Wall-E. But if you continue to fire the fire extinguisher, what would you also continue to do? Accelerate, yeah. So you would really get going if you keep firing the accelerator. So you do, and then you to change direction, and that will work fine, right? The other thing to do is if you're ever lost, it's important safety kids. When you guys are invited to go on Mr. Musk's or Mr. What's the other guy, the Virgin Airways, Garfield, what is it?
Razors.
No, what? Okay, Bezos, that'll work too. Those Virgin Galactic, that's it. I forget his name, but they're all big money guys, and they all want to go into space because I don't know, it's a manly thing to do. Anyway, so but if you ever get invited to go up in space with those guys, first off, think twice. But it is space, so think hard about that decision. But so up in space you go, and if you ever get lost outside their spaceships, because they're weird, you know, they might just forget about you out there. So if you go to the spaceship, be sure before you leave to bring a wrench. Because if you're tied to the spaceship or something and you wander off and a little knot breaks loose and you're like, oh, this might not be good. As long as you have a wrench with you, be sure to try to move the wrench in the opposite direction of the ship and throw the wrench. Newton's third law. The wrench throws you, right? So if you throw a wrench, you will indeed go backwards towards the ship, and then you can scream at the rich people inside the vehicle. Although they won't care because they've got too much money. So, wow, Jim, bitter much? Okay, so moving on from there. By the way, if I ever get invited to go on the spaceship, I'm going. It's a bucket list. So if you guys, you know, make those millions of dollars and make spaceships, please invite me to ride them, please. Okay, so bottom line. This is an old video that shows exactly what I'm talking about, except we're not in space. And there's, well, there's one rich guy here at least. But this is a guy, if you've ever watched the Olympics years ago, this is one of the major Olympics announcers, but like, this is a 40-year-old video. And I forget his name offhand, but I shouldn't. And these two guys are David Letterman and his sidekick, Paul Schaefer. David Letterman was the talk show host late night when I was in college. We adored David Letterman. And then Paul Schaefer was his little friend who, well, he's not his little friend. He's an amazing musician, Paul Schaefer is. Anyway, so they always do silly things, and here's one of the silly things.
It may have to go to EVA, extra vehicular activity, to straighten out his chair. The countdown now is about to begin, so let's go to the launch pad for a look at last-minute preparations.
You all set? Go with what? No, I'm ready. You? Sure. Just move on. 5. Take it to 5. Just go to 5. There you go. There you go.
4, 3, 2, 1, ignition. Ladies and gentlemen, I will describe the scene to you, but I am blinded by the mist. It appears that David Letterman has come out of that mist and has crossed the finish line first. No problem. While lagging badly is Paul Schaefer. Not unlike...
Anyway, just very silly, but that really would work. Go ahead.
Were they using chairs taped to skateboards?
Exactly. They're using chairs taped to skateboards and fire extinguishers, and it worked pretty well. Amazingly well, actually. But yeah, do it at home, kids. Like outside. All right, so because fire extinguishers make a big mess. Yeah, downhill. It'll definitely work downhill. I had to do Newton's third, but it'll work downhill. So yeah, so just a fun little thing with Newton's third. It really does work. There's a ton of videos online with this. I just can't let this go with a little bit of late night history. Good. Okay, now back to momentum. All right. Let me show you. That's right, because I couldn't find my favorite video. All right. Good. So momentum is that. Yeah, I want to do more with this next week, so I'm just kind of introducing you to this concept. But let's do this. That's what I want. Okay, so let's go to kind of, there you go. Conservation of momentum. Now, conservation of momentum is one of the biggest concepts in science, certainly in physics, because science. There are 3 major laws in science: conservation of momentum, conservation of motion, conservation of momentum, conservation of energy, and conservation of mass. In physics, we cover 2 of those: conservation of momentum and conservation of energy. And in chem, we do actually a little bit of conservation of energy and conservation of mass. Okay, that's somewhat you know. Conservation of momentum, basically, it's the simple thing about conservation of momentum is that the amount of momentum before collision is equal to the amount after collision. Conservation of momentum. The amount of momentum before collision is equal to the amount of momentum after the collision. So the amount before is equal to the amount after. I'll do this, and then we'll move on to those topics. And I'm really introducing you to the concepts that we're going to be dealing with next week. We'll be doing some labs based on this and some activities based on this next week. I'll show you something this week. So I get out of the way a second here. So this actually brings us to the video we were looking at a second ago with the different, with the European Space Agency video. I'm sure you guys got that down before I move on. So, have you ever played pool before, or snooker? I love using these sports analogies because physics is everywhere. And you've done so many of these things before, you just haven't necessarily seen this. If you've ever played pool before, or snooker, or bowling for that matter, but it's easier to see on a pool table. Basically, when you start the pool table, you've got a little white sphere, that's called the cue ball, right? And you smack it with a stick. Don't cue stick, right there. Smack it. That's right. So you do the stick, right? Great game. Super cool. Anyway, so that once you do that, that ball has a mass and it will have a velocity that you just impart into it, right? So it's going to have a momentum. So I'm just going to give it a momentum of 12. By the way, there is, because 12 is such a magical number, there is no unit for momentum, which is very strange. It's such an important thing, but we don't have a unit for momentum. It's usually, since momentum is mass and velocity, it's literally kilograms meters per second. But that is one ugly unit, so I just call it a momentum. There's no unit for that. It has a momentum of 12 in this case. As we throw the ball down and the ball hits these cubes over here, it's going to hit the first cube. If the amount of momentum before collision is equal to the amount after collision, how much momentum is going to go? We'll say this ball stops. I'm going to make this easier. We're just going to say this, when this ball hits this ball stops. So all of its momentum, all 12, is transferred to this ball here. How much momentum does that ball have?
12.
Yes, very good. Mathematician. All right, 12 it is. Now it gets far trickier. Now, if this ball hits these two spheres and again stops, and I keep saying stop because if it stops, it has no velocity, which means it has no momentum. All of the momentum is transferred. So if that happens, how much momentum do these two spheres have?
Is it 6?
It is 6!
Yay!
You mathematical geniuses, you! 6 it is! Now this gets a little bit trickier, but not a whole lot.
That's cool.
So notice 12, notice 12, go, you know the last one?
Is it 3, 6, 3?
3, 3, and since 3 goes here and here, and 3 goes here and here, it's 3, 6, 3. Nice. So in this case, it's also 12 again, right? So by the time we're done, the momentum in is equal to the momentum out. Now, if you've ever played pool before, you know that's not the way it works. It's not like click, 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 and then the only 3 balls at the end. In fact, at pool, it's 4 balls at the end speared away, right? It doesn't work that way. But it still works because whatever momentum you gave this ball is still equal to all of these balls, including the ones still moving. After it's done, you can't gain or lose momentum. Now you have friction forces, but in a perfect world, it's all the same momentum. Okay. Even though this ball will be going a whole lot faster than these spheres, right? Because it's mass times velocity. every sphere weighs the same, which means these spheres, this one's going half as fast as this one was originally. This one's going 4 times less than this one was originally, right? Mass times velocity. Okay, one quick question, I'm going to let you go. Okay, 2 or 3 quick questions. Which has more momentum? A school bus that's empty, other than the school bus driver, or a school bus that's filled with 50 screaming 3rd graders, and both of them are going at 30 miles an hour? Which has more momentum? The full school bus going at 30 miles an hour, or the empty school bus going at 30 miles an hour? Go.
The full one?
The full one, because it has more,
Inertia.
well, in this case, because it's moving, it has more
Velocity. Momentum.
momentum. Yeah. Good. All of those things are right, but we're looking for momentum, yeah. All right, so it has more momentum, right? Now, let's do this again. Now, we've got a school bus filled with 50 screaming 3rd graders moving at 30 miles an hour. But we've also got a VW Bug tooling along at 30 miles an hour. Which one now has more momentum? Wait, no, sorry, that didn't make any sense at all. Let's do this again. I've got a VW Bug. One was moving at 30 miles an hour. One is moving at 15 miles an hour. Which one has more momentum?
30.
30 because it's got more velocity. Right? Okay, easy, easy. Now, I've got a rhinoceros and a mouse and probably a very dirty yard. I've got a rhinoceros and a mouse. Now which one has more momentum?
Are they moving?
Anybody want to give a guess?
They're moving, right?
It depends on the movie.
Oh, you dirty birds, you didn't fall for my trick. Yes, it depends on whether they're moving. Pat on back, if you guys were thinking that. Because we need to know its motion. So if I ask you guys that question, your response to it is, I don't know. Because it's got to be moving. Now, last year, I did this exact same problem with the students of what it's doing. And Jeremy,
Yeah, but it's pretty, it's like a
wait,
frame of reference one.
Dylan, do you remember Jeremy?
Yeah.
You probably still hang out with him, right?
Yeah, I talked to him yesterday.
Yeah, so Jeremy went home and figured this out. So the problem was, if I've got a rhinoceros and a mouse, which one has more momentum? Obviously, it's I don't know, because I don't know if they're moving, but if the rhinoceros is pretty much moving at all, the rhinoceros, because of its unbelievable greater mass, is going to have more momentum, even just at less than a mile an hour, it's going to have more momentum than that mouse running as fast as it possibly can. So Jeremy calculated it. He went home and calculated how much does a mouse have, how fast does a mouse have to be moving to have the same momentum as a rhinoceros, basically walking at like 3 miles an hour. And that mouse had to be going at like 2 to 3 times the speed of sound in order to equal the amount of momentum a walking rhinoceros would have, which was fantastically cool.
So basically, the mouse is moving faster than a bullet.
Yeah, exactly. Then a bullet. That's right. So it's literally Mighty Mouse in this case. Yeah. So good. All right. A little touch on momentum. Good amount more with that, especially conservation, because it's a tough and exceedingly important concept for next week. So really this week homework is going to be primarily Newton's third. There will be a quiz next week, youngins, so be sure to, feel free to hand in your homework. There will be a quiz, so be sure to work out what we did at the beginning of today. And of course, homework will be focused on that too to some degree. But be sure to memorize and get that right.
I just turned it in on the website.
Oh, that's fine. Yeah.
Oh wait,
Yeah, I did that.
So,
Either way, it's
do I
good.
still have to turn it in person if I turn it?
No, if you did it online, feel free. Yeah.
I'm gonna.
See you guys. See you later. Bye-bye.
I didn't have any proof that I did it online.
Yeah, that's awesome.
You'd be
I know.
It was the one where it's like, I could only upload like one picture.
fire at my quiz the first thing.
Maybe I haven't looked at it yet.
Yeah, this one, right? Awesome, thank you very much. Yeah.
Yeah.
I see it really well. Loki is.
I picked it before, but saw that we're in the quizzes today and just didn't do any more with this.
Yeah, that's my fault.
But I will try next week.
All right, thank you.
It's fine.
Please.